Geometric sequence and series. A geometric sequence is a sequence of numbers where each term can be found by multiplying the preceding term by a common ratio, also known as R. The nth term of a geometric sequence is given by the formula un equals to u1 times r to the power of n minus 1. And percentage is also a form of geometric sequence. When term increases by p% from the preceding term, their common ratio corresponds to r equals to 100 plus p over 100. And when the term decreases by p% from the preceding term, their common ratio corresponds to r equals to 100 minus p over 100. And the sum of the terms of a geometric sequence is also called as a geometric series. There are two formulas. When r is more than 1, we will use the formula Sn equals to u1 times r to the power of n minus 1 divided by r minus 1. However, when r value is less than 1, we will use the formula u1 times 1 minus r to the power of n divided by 1 minus r. Both of these applies when r is not equals to 1. And the formula for sum to infinity is S infinity equals to u1 divided by 1 minus r and is applicable when the modulus of r is less than 1.
In 7.2, we're going to explore the financial applications of geometric sequences and series. There are two terms that we need to understand here. Firstly is simple interest. Simple interest is the interest that remains the same for each year that you have your money in the bank. Secondly is the compound interest. Compound interest is the interest that is added to the original amount and the new value is used to calculate the interest for the next period. So how exactly can we determine the future value of an investment? Firstly, as we can see here, we can use this particular formula that was obtained from the first section in the formula booklet. And secondly is by using our GDC. In using our GDC, we need to press menu and then press the number 8 and lastly press the first number, which is our finance solver. This is what will appear on your GDC when you press finance solver. In the first section, the alphabet N represents the number of periods. It is a very common cause of error when students mistaken N as the number of years, when it is actually number of periods. Secondly is the annual interest rate section. So in questions, it is common for the questions to give the annual interest rate. So all we need to do is just insert the amount, the value in percentage term in the second section. Next is the present value or initial value. We can understand this present value as the initial money that we have from the start. Think of it as a cash flow. When the cash is going out, the value that we need to insert in the third section is a negative. As an example, when we invest our money from our account to something. And vice versa, when the cash is coming in, insert the value in the third section in positive. As an example, when we receive a loan. Next is payment each period. The way to think about the negative and positive that we need to insert in this section is the same way as we have discussed earlier. Next is the future value or N value. Sixth one is the payment per year. Next, the seventh section is compounding periods per year. And lastly is the payment at beginning or end of the period. Here is an example of the question that may be asked in Chapter 7 in the context of financial application, which is topic 7.2.
Exponential functions and models. In this subtopic, we would like to explore what are the exponential functions and models. So firstly, the general equation is in the form of fx is equals to a times b to the power of x plus c. And the simplest form of an exponential function is b to the power of x. And to know it, all exponential functions have a horizontal asymptote. So exponential function in the form of fx equals to b to the power of x have the line y is equal to 0 as their horizontal asymptote. and this behavior occurs either as x approaches infinity or as x approaches negative infinity, but cannot be both at the same time. This can be seen in both graphs. So the general form of fx equals to a bx plus c has a horizontal asymptote at y equals to c, since the exponential term a b to the power of x can never become equal to 0. The exponential function fx is equal to k plus a to the power of x plus c has the following properties. The straight line y equals to c is a horizontal asymptote. It crosses the y-axis at point 0, k plus c, and is increasing for a is more than 1 and decreasing for 0 is less than a and a is less than 1. The exponential function fx equals to k a to the power of x plus c has the following properties. The straight line y equals to c is a horizontal asymptote. It crosses the y-axis at the point 0, k plus c, and is increasing for a is more than 1 and decreasing for a is more than 0 but less than 1. So, the exponential function fx equals to k a to the power of negative x plus c has the following properties. The straight line y equals to c is a horizontal asymptote. It crosses the y-axis at point 0, k plus c, and is decreasing for a is more than 1 and is increasing for a is more than 0 or less than 1. This can be seen from the graph above.
Moving on to chapter 7.4, Laws of Exponents and Laws of Logarithms. The basic idea of this chapter is that a logarithm is the opposite of a power. In other words, if we take a logarithm of a number, we undo an exponentiation. So in general, the solution of the exponential equation a to the power of x equal to b is the logarithmic function x equal to log b base a, where a, b is more than 0 and a does not equal to 1. The most important thing is to make sure that we get all the concepts right and apply the correct law in our practices and especially during the examinations. A power function of the form y equal to ax to the power of b can be linearized as ln y equal to b ln x plus ln a. A graph of L and y against L and x will have a gradient of b and a y-intercept of L and a, while an exponential function of the form y equal to a e to the power of bx can be linearized as L and y equal to bx plus L and a, and a graph of L and y against x will have a gradient of b and a y-intercept of L and a.
And lastly, everyone, we are going to talk about logistic models, chapter 7.5. The equation of a logistic model has the standard form that has been shown in the slide, where L, C, and K are the parameters of the function, and E is Euler's number. The logistic function is used to model situation where there is a restriction on the growth. It also have horizontal asymptotes at fx equal to L and fx equal to 0. In a logistic equation, fx equal to L is an asymptote to the curve and L is referred to the carrying capacity for the model being considered.